Yes, now comes the next heading that we are going to see is about the half-edge data structure. So in this case, as we had seen in the previous class, how does there's an edge for a particular face, and it has got two surfaces. So if we consider a solid surface, then there is one surface that is going to be outside, then there is going to be one surface onto the inner side, but it is going to have a common edge itself. So common edge, common vertex, all these things, right? But the faces are different. So these things have to be clearly distinguished by the system so that they can understand and it can be represented uh, onto the display screen, right? So here one thing is that, so what happens is that for a half edge is that we are going to have a variable size of face data table, right? A variable size. Okay, so in the previous case where we saw the face table used to be a fixed one. So this was a fixed one that we had. Okay, so this one was a fixed one. So it does not distinguish whether it's going to be the inside face or outside face. It is a face, that's all. Okay, right. So this is the problem with this. So they have come up with, and when we look at this figure, there is only one single edge, vertex, and all those things corresponding to that face, right? So this is what is there into this particular type. So now when we go into this type is that, okay, so we are going to have a variable size of the face table. It is going to vary, right? So it is going to vary. So how does it going to vary? So that means we have to have a doubly linked list. That means the face is there, okay, and it has to have a double link, okay. But that is nothing but the connectivity, right? Okay. Now, now what is this? Now, say for example, a face simply stores the pointers to the starting edge and the list and of the list instead of entire edge, okay, right? And each edge has its pointers, okay, that is connected from the starting point to the next one, okay, in the list. Okay, therefore we have a face table has a fixed number of columns. Okay, now if we reconstruct this, okay, if we reconstruct this, now what is happening? Say for example, now what is this? Now if there is a face f2, okay, there is n number of edges that is coming into this face, e7, e6, and e7. That is nothing but edge 7, edge 6, okay, and edge 2. So all these put together will have the will frame the one particular face, okay, and they will have a particular sequential direction, okay, based on the direction where it can be determined. Okay, so this data is required over here. So there is going to be a face table for this, and how many edges are to be connected to form this face. Now, next thing is that now if we have in this is that what is going to happen? Uh, so we are going to have the face simply stores the pointer to the starting edge of the list instead of the entire list. So it is going to take place. Okay, what is the starting point randomly, and it is going to go in anti-clockwise direction or in clockwise direction until it is going to come back to its starting point itself. So it need not have to store all the data of the all the edges that is going to come into a picture for that particular face at all, right? Okay. So, but another problem that we will face over here is that, okay, now what we will face over here is that, okay, so what we will be facing over here is that now if we take a look at two faces, face number one and face number two from the pyramid diagram. Okay, pyramid diagram, face number one is over here, face number two is over here. So we have edge number two, edge number one, edge number six, right? Edge number seven, and all these things come in. So face number two has got what? Edge number two, edge number six, and edge number seven. So all these three edges put together will get face number two. If we have face number one, what are the edges? We have edge number one, edge number six, and edge number five. So between these two faces, edge number six is going to be a common edge, right? Okay, so that is what is being taken up over here. So if we take up face number one, it is going to have edge number one, edge number six, and edge number five. Now when we go to face number two, it is going to consist of edges made up of number two, 6 and 7. So that will form edge number 7. So the common thing between these two things is nothing but the edge number 6 that we have over here between these two faces, right? So between these two faces, so they may occur a problem. So another problem that we will encounter over here is that when the when F2 shares edge number 6 with F1, okay, there's a doubly linked list that is going to be formed for the face number 2, right? So what should happen is that edge number 6 and edge number 7 has the next edge pointer, and edge number 2 as the starting previous edge pointer. So what it should do is that these common edges should never be taken as the starting point at all for that particular face. It should be something else. It should be any other thing for that particular face when it starts to do that. If it takes this particular common edge itself, then there is a probability of having a problem, right? So that is the reason why these common edges will not be selected as the starting point. Okay, now to solve this problem, if it happens accidentally, then how to do this? So one way of doing this is that what they have come is that they come up with half, where they are going to split this edges into halves. Okay, split one single edge into half portion. Okay, so that it becomes easy to determine what can be done and whether it is going to be in which direction it can be specified. So what they're actually going to do is that, so for the same face table, we have edge number 1 for face number 1. Okay, it is going to consist of E1, E5 and E6. Now if you take up edge number 1, this same one single edge is going to be divided into two halves, which is nothing but H1 and H2. E1 half, first half, E1 second half is that side. So it is going to be like this. So this side is first half H1, this side is going to be second half. So that is what the arrow mark, with arrow mark it is being indicated over here. So simple edge, every edge that is going to be divided into two portions, so that we can easily determine this half of the edge is going to be connected to which vertex and next connected to which particular edge, right? So like that it can be taken care over here. So thereby they are going to split it into half portions, okay, and the directions are going to be opposite for each one of them. So this half of the edge will be in this direction, the other half of this edge will be in the opposite direction. Yes. So now in continuation with this, so now what happens for every edge that is going to be stored, half of the edge list is also going to come into picture, okay, and that is going to be there, and that data is also going to be stored, right? So that is also going to be stored along with what? Along with the directions, and it's consistent also with overall clockwise, counterclockwise sequence for the boundary. So it is going to take these directions in the counterclockwise directions also. So direction for every edge that is going to be splitted into half will have opposite directions, and it will also be in the counterclockwise direction. For every face it will take into account, so that there will not be any kind of clashes. So what will happen in this particular case? Okay, so there has to be a loop that has to be formed. So if I take up this case, if I just draw one triangle, that is one particular face of that pyramid, okay, and it is going to split up into half. Okay, so this is going to be in this direction, this is going to be in this direction, right, and it is going to be in the counterclockwise direction, right? So when it is going to be in the counterclockwise direction, at least one of them. Now if I start counterclockwise direction, it is going to here. So this and this direction are same, right? But when it comes at the end, one of them will be in the opposite direction. The loop is going to close in this particular direction, but this half of the edge is going to be in the opposite direction. So there will be one opposing direction. That is the common rule that is going to happen naturally because of this particular sequence that we are going to follow, right? Okay, right. So thereby what is going to happen? So loops are going to be used to take care of faces having inner holes without adding redundant, okay, bridge edges also. Now why we need this is that, say for example, if we have a face and there is a hole that has to be made. Now for this hole, okay, this edge is a common boundary for the surface that is there, that is a solid surface here, but here there is no material, so it is going to be a hollow surface. Now it has to clearly distinguish this. It has to clearly distinguish this. Otherwise, what will happen is that the computer will not understand whether it is going to be a solid surface or not, which is going to be a solid surface, which portion is not a solid surface, right? So that in that case, what will happen is, if it goes wrong, then what will happen? We will be able to see the hole that has been made, but it will not be hollow, but it will be, rather than that, it will be with material. So that is happening because they don't understand what is a hole, right? The system does not understand what is a hole. So thereby this distinction has to be brought in, right? Okay, so thereby this is where these loops have been brought in specially for this purpose, which is the inside surface, which is the outside surface, to be determined, that is happening in one particular solid part or a particular face. So thereby these loops are required. Okay, so a loop is a list of edges forming an enclosed circle. Okay, so we have to form a loop like this, so it is going to start in the counterclockwise direction. Okay, right, and thus any face is bounded by one peripheral loop corresponding to the external boundary, and several loops can have corresponding internal boundaries, but there should not be any kind of confusion when the system solves this, right? So that is why these loops are going to be brought in, because their directions are different. Okay, right. Okay. The next one is now in. Okay. Now what happens with this? So the face stores a list of loops in a doubly linked list. That means two to list is going to come into picture. So, but what will happen is each loop will have, for the same face, two loops will be there. Okay, and it will have different half edges and having different directions. It will have different directions, right? So that is what is going to have. That is why we get double linked list. Okay, and this two lists have to be linked, because ultimately what is going to happen is that ultimately what is going to happen, even though we have a triangle or a particular face, okay, and even though these edges are divided into half, it has to be linked. This half of the portion of the edge has to be linked with this half of the edge, and this half of the edge has to be linked with the vertex, right? And similarly with the other corner, and similarly with any other corner, and ultimately forming a closed loop. So this interconnectivity has to be there. Okay, right? Yes. So next, what is that? So now, once we have for each loop, the corresponding list of half edges is going to be stored. Okay, and with any number of internal holes, it can be treated without adding any redundant bridge edges. Not required to have any kind of redundant bridge edges at all, right? Now the next thing is that here in this figure, what they have shown is this. So if you take up the same face number 1 and another adjacent face, so it has got half edges H9, H12 and H2, right? And similarly H4, H12, H11 and H14 for face number 2. So for every hole in the loop has a list of half edges in the direction opposite to the peripheral loop. Now if you look at this, if you look at this, now if you look at this, now the face is going to have in one particular direction, the half edges are going to be in the other direction, which is going to be in the opposite directions, right? So that is what is going to happen over here. So for every face, when such loops are there, what will happen? So there may be multiple loops happening for the inside and for the peripheral loop. So they will be opposite in direction. So in other words, half edges of the loop are collected into a list, so that, okay, they are connected to a form a list, so that each half edge has a direction consistent with overall clockwise sequence. So there is one particular sequence, okay, for every loop that is going to be formed, okay, and this has to be viewed whether it's going to be clockwise direction or anti-clockwise direction. We take this by seeing it from the outside of the solid. When we look the solid from the outside, okay, with that aspect, whether it's going to be clockwise or anti-clockwise is what we are going to speak about in terms. We are not going to consider that a person is going to be viewing the solid by being inside the solid. That time the direction will get reversed. So that is not at all taken into care. We have to have a common viewpoint. Okay. So so this so ultimately all this half edges, everything has to fit into the data structure file. Okay, so it has got some of the advantages where over the data structure file, it you now uses only the vertex, edge, and face tables. Connectivity informations for these vertices, edges, and faces are also to be stored. Right, whether we are going to make use of half edges or loops, whether in spite of having half edges as well as in spite of having it as in the form of loops, okay, what is the adjacency, that is the adjacent informations have to be connected, otherwise the solid will not going to be completed. Okay, there will be a lot of disconnectivity, right? There will be a lot of disconnectivity, right? So that is one of the case. So what happens over here, one simple case is that if you are going to make any drawing in 2D form, okay, in 2D form, say for example, let me take up like this, okay, and there is one small opening over here, and the moment that we give to protrude in this particular direction, so that this 2D drawing gets converted into the 3D drawing or the 3D flat form, okay, so that we immediately get one error that there is no connectivity, there is one open loop that is present, the loop is not closed, this message will appear. Yes, that is because of the connectivity is lost over here. Why this suddenly this error is going to appear is because for a solid to be formed, first of all, it has to be an enclosed figure, enclosed drawing. There should not be any kind of opening in any place. So that is the first rule that it is going to check in the when the program is running. Okay, and then once it finds this, how does it find this? So it is going to start from any arbitrary point. Let us start from here only. Okay, this line starts from here, ends up at this vertex, next goes along this direction, and then here, and then here. Then the next thing is that wherever it has started, the ending point has not at all reached that starting point once again, so that immediately there's a error message that is going to pop up, that there is going to be a the loop is not closed. That is happening because of the interconnectivity data between the edge, vertex, right, and the starting point and the loop that it has to follow. Based on these three rules only, we get this error. Otherwise, if this is not going to be followed, what will happen is it is only going to consider the solid, okay, and it will still have a lot of data whether the inside has to be solid fill or not. So it will not have a clear-cut picture over here. So thereby these loops are indirectly used in the system which works in the background. Okay. Now because of this connectivity information, what is going to happen is that the task becomes simple once the connectivity has been established between the edges, vertices and the faces that is provided through the half edges. Okay. So with this information, we can go about it to easily connect it, right? Okay. And yes, so with this, we'll go to the next one. So, okay, there is another way what they do is that, so say for example, they take up, we have one particular cube like this, okay, a rectangular prism, okay, where now say for example, we are going to go with the vertex. I want what are the details for this particular vertex V1. Okay, then what is going to happen again, same half edges rules are going to come into picture, where it is going to see which are all the things that are connected to this V1. So first thing is that we are going to have one half edge in this particular direction and another half edge in this particular direction. That is one of the connecting connecting edges to this V1. So the parent edge for this will be taken up from the adjacent edge, which will be called as the previous H1. Okay, it will be taken up randomly, which will have the previous H1. For this half of the parent edge, okay, there should be one more opposite edge that has to be created, which is going to be the new H2, so that we are going to get the complete detail of the V1 vertex. So this is the connectivity data that it has to store, right? So that is what is these two lines. So once we get, whenever we want any edge details or vertex details, this search is going to start like this. Okay, right? So the search is going to happen like this. So what are the steps as just mentioned? So the first step is that it is going, what is the vertex or the corner that you want? So from there, which is the starting vertex? So any one of the half edge that it is going to take one, denoted by H1, right? So for this, it should have a previously half edge, which is denoted by previous underscore H1, okay? And also selected as its parent edge becomes one of the edge connecting to the V1. Okay, right? So the conjugate of this will be for the of the previous H1 will be the, that is the opposite direction for the loop to be closed, will be the new H1 over here, right? So and this process is going to continue until the conjugate halves of original H1 is reached. So this process is going to form until the loop is going to be closed for the, until it comes back for the entire solid to be in again in H1, because that was the starting half of the edge that started from vertex V1, right? Okay, so now let's go to the winged edge data structure. Okay, this is a little bit easy to understand. So where what we are going to do is that in this particular type of data structure, what they are going to do is, okay, this is also a half-edge data structure, okay, but stores the list of faces and everything linked to its edge. Okay, so here the face plays a major role in describing the solid. So in contrast with that, but faces are found by the edges that play a major role in the winged edge data. So why this is that in the previous thing we took up only with respect to the faces. So the faces are connected, are formed by having the edges connected. So the edges are dependent upon the vertices, right? But here in the wing edge data structure, what we need is about the details of every edge that it is going to be there. So it has to be stored in the data structure file. So how is this going to happen? So each edge stores the face sharing, okay, that is the neighboring edges, right? And any of the vertices of the edge, okay, and the vertices at its end. So if we draw any one line for a particular face, this is a common edge that is going to be shared between this face and this face. So for this edge, there has to be one corner here, there is one corner over here, okay, and this is going to be the common edge. So this data will be there in F1 table also, will be in F2 data table also, right? Okay. So next is that this edge data are needed. So if it has to identify whether it's going to be belonging to, whether we have to construct with respect to phase 1 data, what should I take? If it is going to be the same edge, that is going to, since it has been a common edge with respect to F2, then what it should take, right? So how is it going to identify? There's another way with respect to considering the edges, but not with respect to giving a role, major role for the face that is being found. So how does this take place? Let us see that. Okay. So here, what happens? Yes, the lines of the edges of each face is not explicitly stored in this data structure because it is derived from any one of the face edges and its neighboring edge. So every edge details are not stored at all over here. Okay, right? So the problem encountered with varying number of edges for faces without introducing the linked list. Okay, and consequently, the half list will also have a problem which has to be reintroduced into this. So how to do this? Let us see. So how does this is going to take place? Let us see over here. Yes, yes, not here. Just a moment. That. Okay, all right, fine. So I'll redraw it. Okay, so all right, yes. Okay, so now what is given over here? Now let us consider that we are going to worry about this particular edge denoted by E1. Okay, right? So we are going to see about this. So this E1, the starting point is V1, ending point of this line is E2. Sorry, V2. Okay, starting point is V1, ending point is V2. Now for this edge, which are the adjacent edges in this particular solid? We have E3, we have E2, E4 and E5. So the adjacent edges for this particular edge, okay, will be all these four edges that will be coming into picture, right? Now how do we distinguish this? Now if we apply one particular direction such that now this edge is going to start at V1 and this is going to end at V2, right? So it is going to start from the bottom V1 and end up over here. Okay, now we are going to have this adjacent edge E3, E4, sorry, E2, and here we have E5, and here we have E4, right? So now with respect to this in this particular direction, it almost looks like a wings of an aircraft. Okay, this is nothing but one wing, and this is another wing, and here also another wing, and here also another wing, right? So that is the reason why this has got winged edge data structure that has been found. So this wing structure has been obtained because of the edges that has been taken into picture. So thereby it is called as the winged edge data structure. Okay. Now it is going to store this data. So now if we look at this, okay, and if we just impose the same thing now, if you are going to take up the same shape as the we are going to just move our hands and legs very much similar to form the wings of an aeroplane. Okay, so that now if we are going to stand here in the upright direction, so our right hand will stretch in this particular direction, our left hand will stretch in this particular direction, and at the same time we can move our right leg here and left leg here in this particular direction. So thereby what has been called here is that this E3, this particular line is called as the uh, right arm edge. This is the right arm edge because this is the right arm, okay, and it is within the arm structure, and it is the right arm that we are going to use this, right? So this is called as the right arm edge. So this is going to be followed by, if we stand up in the upright direction and we can move the our left hand in this particular direction, so this is going to be called as the left arm edge. Okay, left arm, and that is going to be indicating what? The edge. So it is called as the left arm edge. So similarly here, this is going to be the right leg edge, and this is going to be left leg edge because our right leg can move be pointed towards this direction and left leg to be pointed towards this particular left direction. So this is going to be right leg edge, and this edge is going to be called as the left edge, left leg edge. Okay, right? So that is what is actually being described in this particular paragraph. So that is what is actually being explained over here, right? So if we have just like a fuselage of an aeroplane, we have four edges over here, E2, E3, E4 and E5 suggest the wings, okay, and these wings are connected to the E1 edge. That is the edge that we are going to consider. So now over here, what is going to happen? So now if you look up for this particular direction, okay, for standing in the upward direction, so the edge is going to be directed from vertex V1 to V2, okay, and now when we stretch our arms and legs, like where we are flying. Okay, so our left arm will touch the edge V2, that is just move it up. So our left arm will move towards the edge E2, our left arm over here, okay, and our right arm will touch the edge E3 in this particular direction, and similarly for right leg, okay. So therefore, yes, so this is for, yes, E4, our left leg will touch E4 here, and right leg will touch the E5 in this particular direction. Now, if we reverse it in the opposite direction, then everything will change. Then all the sequence will change, and that is what is given in the in this in this particular paragraph over here. Okay. Right. So now what happens is that in addition to specifying the connectivity, okay, we are also going to in terms of winged edges, we are also need to specify the connectivity of the faces and edges. Okay, so both that is also going to be formed. So this is why each edge point sharing two faces. Okay, each edge point is going to share two faces. So every edge will have a two faces at least. Okay, that will be the minimum one. Okay, so these two faces are stored under different names for the same reason that the winged edges have different names. So there will not be any confusion once we have the different names, right? So that there will be a clarity. However, the solid is going to be rotated, moved, or whatever is going to be done, the names are going to be different. And this is what was introduced in the form of loops. Okay, right? So there we are going to have it in the form of in different names so that it is going to be clearer one, right? Okay, right. So next one is that what they have done is that they're going to go in for loops. So apart from this, they'll form some loops for this, right, in the counterclockwise direction, in the counterclockwise direction, right? So this edge direction is over here. So for this particular phase, it is going to be in the counterclockwise direction. This edge and this phase counterclockwise direction are going to be opposite, so that it's going to be a different phase number. And but here this direction and this phase is going to be in the same direction. So this will keenly observe it, get the details as this is going to be representing a different phase, right? Even though it has got a common edge. So that is why the loop is also going to be introduced over here. Okay, right? So yes. So that is what is actually being told over here. So the loop is going to be formed over here. Okay, L1 as it is the left loop, and L2 is going to be the right loop. So each loop points to the edge belonging to itself. Okay, and the starting edge from which neighbors edges are traversed to give a list of edges that is going to, as the loop is going to travel, right? So it's going to take up all the data connecting whenever this loop is going to circulate. Okay, and connecting edges are going to be, I mean, the edges that it comes across, that particular data will only be fetched for the deriving of the half edges, so that all the other edges details are not to be required over here. Okay, right? So that is what is going to happen in this when we introduce the loops in this particular case, right? Okay, so yes, we shall stop here for today.